Hi, I'm Jamie. This is Dead Dodge Garage, and this is a 225 Slant 6. If you know Mopar, then you know the Slant 6. These engines were used in basic transportation type vehicles for decades. A Slant 6 was the only engine you could get in an A-body from 1960 through 1963, either in the short deck 170 cubic inch configuration or in the taller deck 225. The Slant 6 was engineered specifically to work with that A-body. It was canted over at an angle to allow for a lower European-style hood line, and the water pump was moved sideways on the block here to keep the block compact. Also, the Slant 6 only has 4 main bearings, unlike your typical inline 6, which would have 7, for the same reason. It's supposed to be short in length and low. It was also intended to be lightweight. Originally, the Slant 6 was meant to be made out of aluminum. Some were, but most were cast iron like this one. I've done videos in the past on the aluminum Slant 6 if you want to know more. Although they're largely known to be industrial-type, bread-and-butter economy engines with no sporting pretensions, there were high-performance Slant 6s from the factory. Not quite this high a performance, but still. Just about all performance Slant 6 modifications known today can trace their roots back to the Hyperpack. If you've seen the gigantic Aussie Speed Hurricane manifold, it's based on a Hyperpack. If you've seen Doug Dutra's Dutra Dual exhaust manifolds, where the exhaust is split into 2, that's copied off the Hyperpack. There are other things you can do to a Slant 6 to try and make horsepower. From experience, I can tell you this is a bad idea, but it is kind of fun. But the vast majority of Slant 6s were super basic, cheap economy engines, just like this one. As with just about all engine families, I suppose, it is possible to squeeze some extra horsepower out of a 225 Slant 6, and that is what we're doing here. Before we move on with the particulars of this build, I do have to recommend you go watch Uncle Tony's Understanding the Slant 6 video if you want to know more about the basic engine architecture and things that can be done with them. I learned a lot from that video. I think I've watched it like 4 times. It's packed with great information, so go check that out. Here's another great resource for Slant 6 info. I mentioned Doug Dutra a minute ago. He is like the guru in the slanted world. He wrote this book, Chrysler's Slant 6 Engines, How to Rebuild and Modify. This is one of those workbench books, and it is full of nice full-color pictures. There is an insane amount of information to learn in here. If you're thinking about hot rodding a Slant 6, or you just kind of want to know more about them, I highly recommend you pick this up. My friend Vivian has a 1963 Dodge Dart GT. Of course, in 63, the only engine you could get in a Dodge Dart was a Slant 6, and that's what's under the hood now. It's actually been rebuilt. I don't recall if it's the original engine or not, but I do know the cylinder head has been gone through, and it has a custom ground camshaft from Delta Cams. I've done a good bit of work on that Dart in the past, including removing the transmission for a rebuild, overhauling the 7 1/4 axle, I think, or did I imagine that? Installing a dual circuit master cylinder, and tuning. In fact, I've tried to tune that car several times, and it's kind of just never been right. I finally did a compression check after a few different rounds of this, and learned that the compression in the 225 Slant under the hood is less than ideal. It is not consistent. There are a couple holes that are pretty weak. It's just tired. It's done a whole lot of road miles. We made the decision to get a different short block to rebuild. This allows the car to continue to run and drive while this is done. If we're going to get a different engine, we had our choice of which Slant 6 to go for. Well, we've chosen the best one. Because the Slant 6 block was originally intended to be aluminum, there's a lot of extra beef built into this design. Although the iron block is not identical to an aluminum block, it's very similar, and it shares all of those basic characteristics. The original forged crankshafts are also very beefy and very heavy. Look at the size of the counterweights on these things. It's kind of nuts. For this build, instead of getting another one of those old school engines, we've opted to go for the best one. I showed the teardown of this particular 1983 cast Slant 6 in a previous video some months ago. The nice thing about these, lightweight. The block is considerably lighter than the old school block. They took a bunch of extra material out from various places. Cast crankshaft started in the Slant 6 in the late 1970s. I don't know if they got this ultimate lightweight design at that time, or if even more was taken out of these counterweights in the early 80s when the block was changed. What I do know is that although this is a cast crankshaft, it's plenty strong for our application, and it's a whole lot lighter than the old forging. Reducing the rotating and reciprocating weight inside your engine in general is a great thing. The less weight you have to drag around and accelerate, the better. You're freeing up horsepower and getting a more responsive package in the deal. Apparently, the original 225 Slant 6 from a 63 Dart GT was rated for 145 horsepower. That would have been a gross rating, as was typically used in the day. In the 1970s, power ratings were switched to net. That included losses from various accessories, and these numbers would be reduced significantly. We're going to be doing a little bit of hot rodding, trying to squeeze some more power out of this 225, but there is no way we will ever make enough power to hurt this cast crank. The not so great thing from a performance perspective about these 80s engines, they came with hydraulic lifters. A really goofy hydraulic lifter setup, in fact, because they had to be lubricated through the push rods from the rocker arms. The good news is the older, solid, flat tappet setup fits right into the hydraulic block, and that is exactly what we're going to do. We're going to use the camshaft, the lifters, in order, and the cylinder head off of Vivian's existing engine. These components will go right onto our later block, no problem. Now you may have noticed Dale's Demon in the background instead of a white 63 Dart GT. Because I don't have that car yet, or the engine out in pieces, I can't exactly finalize this build. What we're going to do is get it as ready as we possibly can before the car gets here, so hopefully from that point it's a relatively straightforward and quick process. Before we get started on that, I do want to tell you about the one big thing we had done at the machine shop while the block was there. Obviously it got cleaned, it did get new cam bearings, and you'll notice it doesn't have core plugs. That is because Johnson didn't have a cam to test these bearings. I had to bring it back here and put the old camshaft I took out of it in there to make sure it spun freely, which it does, so we're good. If we had to do any cleanup sanding on those bearings, Johnson wanted to still have the ability to clean this block before he put all the plugs back in it. Anyway, the main operation they took care of was milling the deck, the surface where the cylinder head mounts. This is done to bring the compression ratio up. Now, you might think, if you've built a performance V8, that a great way to do this would be installing a set of aftermarket pistons. On the Slant 6, the only aftermarket pistons are a stock type, and they're still way down in the bore. Here's one of our replacement pistons now. This is a 30 over slant piston from Silvolite. You'll notice it does have an offset pin. It has all kinds of details that are exactly the same as stock. If you want to rebuild a Slant 6, you have precious few choices for pistons. You could spend a bunch of money having something custom built, but I don't really see the point in that. Especially when milling the deck is an option. Because this is an inline engine, we don't have to worry about intake fitment between two different heads. There is essentially no downside to taking a big cut off of the block. I've read about people cutting them as much as 100 thousandths, although apparently that does tend to lead to cracking into head bolt holes, which we don't want. I was informed by Johnson that each cut they took with their machine would only remove about a half a thousandth of material. They decked this thing 60 thousandths, which means they took 120 passes. This is a street engine, and we're not trying to make a bajillion horsepower or run on race fuel. We're shooting for somewhere around 9-to-1 compression. By cutting the top of the deck, we're raising the piston in the chamber effectively. Currently, we don't know how much of a corresponding cut we're going to take off of the cylinder head to reach our compression goals. We'll get there later once the head is off. Anyway, now it's time to finish the prep on this block, and then I think we could probably install a crank, some rods, and pistons. We do need to check ring gaps still. There may be some filing to do there, and we'll go through all of the other components that I'm installing today. Before any of that can happen, cleaning. Step one here is to install those core plugs, the oil galley end plugs, and also the rear cam plug. I cannot show these things on video without commenters disagreeing over what they're called. Understand the reason they exist is to remove core sand from a fresh casting. They are not here for freeze protection, and if you're relying on them for that, well, don't. There are various ways you can install these. They can definitely be knocked in there dry. I've done that in the past. But I really don't want them to leak, and so I'm going to hit them with a little bit of aviation forma gasket. You could also use silicone, but yeah, I'm going to do this. Typically, to drive these home, I will find a socket that closely matches this inside diameter of the plug. But today, I'm going to use bearing and seal drivers because I happen to have the right ones for them. Core plugs? Core plugged. So shiny. It's like jewelry. Had to loosen one arm on the back of the block here. 3 out of 4 ain't bad. I got the rear cam plug put in. Also have aviation sealant on that. This is the rear oil galley plug. I installed that with some Teflon tape. You can see the oil galley or oil gallery, whichever term you prefer, goes down the outside of the block here. It's in this cast-in area, which is fed through 2 ports, one to the rear section, one to the front section, that comes out of this area fed by the oil pump itself. On the original design of the Slant 6, there would have been cast-in passageways from that galley up toward the lifter bores. But these were never actually utilized. You could see the cast-in areas on the original aluminum blocks, but the iron block never had that. This is why these late blocks had hydraulic lifters that were oiled through the push rods from the top, because it was the only way they could get pressurized oil to them. Yes, they probably could have revised the casting and added these passageways back in, but they didn't want to do that, presumably for cost reasons. And there's the forward galley plug. As you can see, the camshaft is right inside the block alongside that oil galley. Of course, the cam journals need to be lubricated from that galley, and they are through these holes in the bearings. But if you look in there, you can see that area behind the cam bearing, at least on the forward one here, is just kind of open. This is a big passageway that comes down here to feed the main bearing. Looking at the second main bearing, you can see this big cast-in bulge. This is the oil passageway that passes by the cam and comes down to the main bearing. These slants have a super simple oiling system. It's those 4 passageways that lubricate both cam journals and the main bearings, and one more hole. You might be able to see there, I'm actually shining a light in it right now. This is the oil hole for the top end, and it comes from the rear, the number 4 cam bearing. Here's a look at that hole from the top. It comes through the deck surface right here next to a head bolt. And if I remember correctly, it actually intersects with that head bolt inside of the head, and then there's another hole that goes up to the valve train. With all the block prep done, it's now time to check our ring end gaps. This is a 30 thousandths overbore slant 6, so it has a bore size of 3.43 inches. Using a ring gap factor for street or light performance use of 0.004, I come up with a desired ring end gap of 14 thou. I've got all of our top rings dropped in place, and well, they're already there, like perfectly across the board. So I guess we'll just be putting these in. All of the second rings are also bang on at 14 thou. This box of rings says Engine Tech on it, but inside the bags say Hastings. Nice. And you can see the moly coating there on the side of the top ring. I gave the bores one more wipe down before assembly. Here's what I got. And now I've got the block flipped over for crankshaft installation. I did also clean the main saddles here. You might notice a little bit of flash rusting. Good thing that never hurt anybody, because everything that comes in this shop ends up with a little flash rusting. Anyway, time to install main bearings. Of course, because this is a Slant 6, there are only 4 of them. Now, a typical slightly heavier duty inline 6 engine would have 7 main bearings, 1 at each end, and then 1 between each piston. For the Slant 6, they deemed those extra main bearings unnecessary because this engine makes almost no horsepower, and in the interest of saving space and creating a short package, they omitted 3 of them. Various internet experts will tell you that the lack of extra main bearings makes the Slant 6 absolutely worthless, explosion-prone, and pointless to try and make horsepower with. Of course, as devoted Mopar nutjobs, we know better than that. When I pulled this crankshaft, it looked absolutely beautiful. So this thing got a basic polish job to clean it up, and that's it. I do still need to knock the lint off this thing. Because of this, we're using the standard size sealed power 5070M main bearings for this engine. During the teardown of Evans' aluminum Slant 6, I learned that the aluminum and iron slants used different oiling holes, and that many of the main bearing sets will include both of them. This set only has the one. Hopefully it's actually the one we need. I think I say this in every video, but make sure you clean your shiny new parts before you install them. Take these bearings, for example. They've been bouncing around in this cardboard box for quite some time. They're kind of covered in little bits of fiber. Here are the front 2 upper main shells with their grooves and oil holes installed. Indeed, they are correct for our iron block, but it is interesting, the holes in the block do not fully line up with the holes in the bearings. I think that's why the holes in the bearings are slightly oversized. Note that one is offset that way, and that one is offset the other way. And here are the rear 2 upper shells installed. Note, even though there are only 4 main bearings here instead of 5, the thrust surface is still found on the number 3, just like in Chrysler V8s. The main caps are clean and the corresponding bearing shells are installed in them. And last but certainly not least, the upper half of the rear main seal. Note, of course, the lip is facing inward. I was advised recently that it's a good idea to pre-lubricate the sealing surface where that seal is going to ride on the crankshaft. I've literally never done that. And I've built a lot of engines, and I don't think any of them have ever had rear main sealing issues, except Tracy's 440, which is this whole other thing. Regardless, I guess I'm going to start doing that. The Felpro instructions on this package said that grease should be used if the engine won't be started for a few days. Yeah, it's going to be more than a few days, so I guess we'll do that. The rear main seal actually goes in a cap, much like a big block Chrysler engine. I need to clean this thing, so that'll be a future Jamie problem. The crankshaft is clean to my satisfaction, so at this point, I suppose we can install it. At least after the main bearings are pre-lubricated with some engine oil. This is what I always use for assembly. Crankshaft, main caps. As always, I lined these up, started the bolts, and then I tapped them home lightly with a hammer. I was told in a comment on a recent engine building video that I should use a dead blow instead of a typical steel hammer. Well, there's a reason I don't. Dead blows tend to leave little bits of plastic behind. And eventually, once they're ruined a little bit more than this one is, they start leaving little bits of steel shot behind. None of this should be in your engine. I would never suggest that you wail on your cast iron main caps with a hammer like this. Tap it gently into place. It shouldn't take any more than that. Taking these bolts to their first torque spec, before you torque your thrust cap, the number 3, make sure you set your thrust. And the way you do this is by gently forcing the crankshaft forward to align those thrust surfaces with a screwdriver or something like that. I always delicately tap it in between one of the throws, the counterweights, and the block, just like this. Now I'll torque this to its first stage, which is something like 35 foot-pounds, and we'll check this crank for thrust or end play. With the mains run to their first torque stage, this thing spins fantastically well. And here is our thrust. I am going to measure that, but you can see we've got some, but not a lot. That's good. Apparently the desired crankshaft end play spec is 2 to 7 thousandths. We appear to have 4.5 or 5. So I feel good about that. Main bolts are torqued to their final spec of 85 foot-pounds. That's the same as a small block Chrysler engine. You'll notice I did paint mark these with a little dab of yellow. That's so I know I've done it and I can sleep at night. This crank spins perfectly. Note, I did not check oil clearances. This is a standard size crank. It's been polished, so that oil clearance should be a little bigger than it was stock, but not much. It's a standard size bearing. The fact that the thing spins perfectly and feels really nice tells me the clearance is fine. I own all of the equipment necessary to check this, but I've proven time and time again I'm no good at it. Yes, Plasti-Gauge exists, and if you're worried about your oil clearances, use it. Now I'm getting piston and rod assemblies ready. Number 1 is totally good to go. I've got the rings all in place. I spiraled the expansion section for the oil control ring and both of those into place by hand, and then I use a ring expander like this for number 1 and number 2. I used to spiral those too, but apparently that's a bad idea. This has already been cleaned, the rod bearings have been cleaned, the areas where the rod bearings sit have been cleaned, and the bearings are installed in the rod and cap and ready to go in. Quite some time later, we've got 6 completed rod and piston assemblies. These are ready to install. Obviously, I'll have to pull the caps back off one by one, and they do need to be coated in oil. Because this is a factory type piston, it is a press fit pin. There are no clips here. So these were assembled by Johnson. You can see obviously there is a notch that points forward, and the factory positioning points these notches at the oil gallery side, the passenger side of the block, and a squirter hole at the passenger side of the block as well. This is supposed to lubricate the cylinder and cool the skirt of the piston somewhat. In the book, Doug Dutra actually recommends installing the rod and piston assemblies with the block on its side. I'm not going to do that. I'm going to compress the rings with a ring compressor and stab them in from the top as I always do. I've got the number 1 journal down now. I will be rotating the crank using the crank bolt I've installed temporarily so that every journal that corresponds to the piston I'm dropping in is down. I'm probably not going to use journal protectors on this one. I could, but these studs are going to be very far away from the crank when I'm done installing the rings. I don't think we're going to have a problem here. Everything's covered in oil. The bore, the piston, the rod bearing, the ring compressor, the deck a little bit. It's going to be fine. We'll clean that later. I'm a little concerned that because so much material was removed from the deck, there's not much of a chamfer at the top of these bores. That's a tapered area that helps guide the rings into the holes. Really good chance I catch rings under the compressor above the deck, like multiple times here. But we'll see. Yeah, immediately. Rod bearings shooting out the bottom is a recurring theme too. Why? Can't have anything nice. At least the oil rings are in. Cutting a new chamfer into the top of the bore might have been a good idea. A little late now though. Thank you. Sometimes when these put up a fight while you're trying to install them, you will have the pre-installed rod bearings shooting out the bottom, which is not great. I get to reinstall that upside down. Maybe this is why Doug puts them sideways, I don't know. Now we just slide that down onto the journal and hope that it's kind of straight. There you are. Wait, there you aren't. There you are. It's amazing how far down these have to go. The stroke of the 225 is something else. There's the rod cap for number 1 installed. I just snug the bolts. We'll roll this thing over again and torque all of these later. Here's the number 1 piston lined up at TDC, and you can see how far down in the hole that still is. Now remember, we've had this deck cut 60 thousandths. Here's approximately 60 thousandths of feeler gauge. That is how much farther down in the hole it would be if we hadn't cut the deck. Looking at this, I'd estimate it's maybe another 70 thou down in the hole, which again, pretty significant, but this is a major gain compared to where it would have been. Bringing a piston to zero deck where it's perfectly flat is a common procedure these days so we can get something called quench. I've discussed quench in previous videos. This is an effect that is brought about by the interaction between a flat top piston close to zero deck or at zero deck and a closed chamber cylinder head. Of course, the Slant 6 doesn't have a closed chamber head. We will never have quench in this situation, so that isn't as much of a concern. It's really just the compression ratio we're worried about. Oh, I wanted to point this out. You can see the impression of a plate and these like screw heads or rivets or something on the side of the block. That is from a patch on the mold that casts these engine blocks. How neat is that? Unfortunately, I've run out of time for the evening. I do need to get these next 5 pistons and rods dropped in and then torque all of the rod nuts before I can call this short block complete enough to get the dart down here and gut it like a fish for the rest of the pieces we need to assemble this engine. There are a couple more things I could do, like go through this oil pump. Also do the rear seal cap. Also clean stuff. But I gotta go eat a burrito, so all of those things and more are gonna have to wait for the next installment. I know a good few people are anxiously awaiting Performance Slant 6 stuff on my channel. Well, it's happening, so tune in to future Engine Wednesdays when we'll do more stuff with this. I also have a second lightweight 1980s 225 Slant 6 build in the works, so I guess we'll see that too. Anyway, hopefully you enjoyed this. If you have any Performance Slant 6 questions, feel free to drop those in the comments. I see, well, most of those these days, and I will answer questions as is possible. Until next time, as ever, thank you very much for watching. And remember, core plugs. They're core plugs. But I don't really care what you call them. Oh, and in case this video looked kind of fuzzy, I got aircraft sealant on my camera.